Good afternoon and good morning, everybody. Welcome to the Deep Casing Tools webinar. Today we're talking about turbine-powered reamer shoe. In specifics, we're talking about the TurboCaser. My name is Malcolm Spiegel. I am the Well Engineering Manager for Deep Casing Tools here in Aberdeen. And with me today, instead of Faisal Zaidan, who is currently running a TurboCaser offshore for us, we have Callum Law, who is our operations engineer based in Aberdeen, and we have Emma Wood, who's running the presentation for us. She is our marketing coordinator. So during today's presentation, there is a question and answer available. You will see in the bottom of your screen on the ribbon, there is a question mark in a speech bubble. You can write your questions in there to us at any time, and we will answer them at the end of the session. During the presentation as well, there'll be a couple of short, very quick poll questions, which we will be asking you. No experience required of the tools. It's mainly about whether you've actually used or experienced them before. Okay. So as I say, welcome to the webinar concerning the TurboCaser technology from Deep Casing Tools. We have two types of turbine reamer here at Deep Casing Tools, the Turbo Runner, which is a final string, non-drillable reamer shoe, and we have the TurboCaser, which is the subject of today's webinar. As you can see from the drawing on the screen there, very similar to a conventional piece of casing shoe equipment, but from the outside, but obviously very special reamer shoe on the end, which is a high-speed, low-torque reamer, purely hydraulically activated by pumping fluid through while running into holes. So the idea with this technology is it is used to remove any obstructions that might be in the annulus while you're running your casing. The TurboCaser, as mentioned, you can drill through once you've got it into position. So starting from right to left in this picture, we have the casing liner connection. We can make any kind of connection to any kind of casing that you might need before we send out the tool to the rig site. From there, we go to the fail-safe rupture disc and bypass system, which I'll show you more about in the next slide of a cross-section. Then we have the main turbine-driven hollow shaft, or we call power section, which houses the equipment, the rotors and stators that are used to actually provide the mechanical movements to the turbine reamer head that are moved by the flow of fluid through them. There is then a non-rotating stabilizer and then the reamer head. So the only part of this equipment that moves is the reamer head, which has the PDC cutting structure, and there's a convex shaped nose which allows it to ride over ledges or micro doglegs that you might have within your annulus. Oh, that's the wrong. Why is it done that? Sorry, I've gone to the wrong slide. Here we go. So here we have the cross-section of the TurboCaser showing the flow path from left to right through the tool. So we start with the fluid coming in through the top sub. Normally around this area we will have a filter which will filter out any extraneous materials from the mud. In the past we have had experience with some very strange items being caught up in the mud system, such as tie wraps or electrical cables. These will be filtered out at this point. The flow then goes past the burst disc assembly and is routed around the outside of the shaft on the internal wall through the rotors and stators, so 40 to or 25 sets of rotors and stators that are then mechanically, hydraulically rotated, giving the mechanical force that is then transferred down to the reamer head. You can see the fluid then flows down through the stabilizer section and out through the reamer. The burst disc assembly itself is there for safety. If you have a blockage of any kind, it will be activated by pressure differential, which will cause the burst disc to rupture. in this case, the fluid flow will then go straight through the main hollow shaft of the runner. So you would lose the ability to rotate, but you'd still have a flow path in the worst case scenario. The turbine head rotates, and of course the rotation that you get from that depends on the flow rate and the mud weight that you're putting through it, but it is a high rotation system. The main analogy that we like to use here is that of a dentist drill. It is extremely fast, and we'll show you some photographs later on of the tool in action. One of the defining features of using a turbine reamer instead of a PDM motor is that with this turbine, because of the high rotation, there's you see a pressure increase as the turbine starts to rotate. So if it's free, it will rotate quite quickly. As soon as it meets the restriction or it becomes stalled, the pressure will drop as the flow restriction decreases. Once you've got your TurboCaser down to depth, you can also cement through conventionally, absolutely no issues. And because you also have the turbine head operational during the cementing, it provides a secondary cement shear, which helps to get a nice uniform cement job. As mentioned previously, the TurboCaser is also drill through. So you would use your normal drilling BHA PDC bits to drill out the top assembly and then the turbine reamer. If you have over displaced your cement or you have green cement, you can lock the reamer by putting weight down on it to stop it from rotating when you go down with your drilling BHA. So the times you would use a turbine reamer, as mentioned, if you have any cuttings beds or issues with hole cleaning left behind from the drilling runs, or you have hole fill at the bottom of the hole, you can use the reamer to agitate the cuttings and help you move past those and hopefully get them out of hole. If you have any ledges in your annulus caused by hard formations or swelling shales or things like that, it would also help to get past or remove those from the annulus. It can help to smooth out micro doglegs caused by directional BHAs or any deflections that might have occurred while drilling. It can also be used to remove excessive mud filter cake from the sides of the annulus, which will help to ease the passage of the casing down. It's especially good in undergauge sections. As mentioned, you might have some swellable shales, or you might have formation creep or something in certain sections that cause a bit of a squeeze on the annulus. Again, using the reamer here can just help to smooth the transition of the casing down. And we're also looking at removing the necessity for excessive hole cleaning. Obviously, we know it takes a lot of time and money to be able to perform extensive hole cleaning or under reaming or hole opening at the end of sections or during drilling, and using these turbine reamer tools can help to remove that from the operational sequence. So we'll now go to our first poll question with Emma.
Thanks, Mal. Yep, you should now see the poll question of, have you used a turbine-powered reamer shoe previously up on your screen now? If you could all take some time to answer that now, that would be great. Now, thank you to those who have answered. We have 80% have said no and 20% have said yes to that poll question. I'll now hand you over to Callum, who will continue the webinar.
So yeah, this particular slides now go on to describe a little bit about the well in question here that we have. And this is the plan and the vertical view. So you can see on the right hand graph is the well profile here, the vertical view, and it's also showing the formation tops of the specific formations, which is quite, some of these formations here in the Middle East are quite challenging, to say the least. So you can see at the end of the section there that it goes into horizontal. So this is the schematic from this particular well. You can see it departs the 33/8, I think around about 4,600 feet, and has a section TD of 14,900 feet. So all in all, a 12.25 section of 10,200 feet, which is quite a step out for a 12.25, quite a distance for a 12.25 section. On the next slide, we have the challenges, basically, with these various challenging formations in the Middle East here. While they were drilling the 12.25 section, they got stuck 3 times, so had to pull back and sidetrack all 3 times, and then eventually sidetracked on the 4th one successfully, and pulled out the hole and ran the 12.25, the 9 5/8 casing. So each time, you can see the Mishrif and Salabi was kind of Naruman in particular was quite challenging formations to drill through. On the next slide. So, with all that various data and information that we got from the well and from the client, what we do is we make a job preparation. In other words, we try and simulate the hydraulics running of the tool with the hydraulics calculation. We use software from Merlin TDH, and we find that as an extremely good software to use. It seems to be fairly accurate in what we've been doing so far. So as you can see on the left hand side here, the graph on the left hand side shows the standpipe pressure with the 5 flow rates that we've given for this scenario, going through the various formation tops, so it's versus the depth. Okay, and on the right hand side is the ECD with those same flow rates. So this is we would normally download this and give it to the drilling engineer and team, and then they would then give it to the offshore team to have it by their side just as a reference. So when the tool goes offshore, it's then picked up and we do a surface function test. Now, on this picture, you can see where each component actually is in relation to the tool itself. I know Mal mentioned it before, but again, we've got the connection that we provide prior to going offshore, so it's there's no real crossovers required. The burst disc and diffuser system is just below that, and then we have the power section, the stabilizer, the external stabilizer, and the reamer nose on the bottom with the PD cutting structures. Now these PDCs are very, very small, and the shape of the nose is bullet shaped, so it allows for riding over ledges, but predominantly as well is the fact that it will not drill a new hole. It doesn't have that enough torque, and the shape of the tool as well is such that it's and the small PDCs is non-aggressive, so it will not drill new hole. So on the next slide, on this is the profile that we're speaking about. So as you can see, there's two TurboCaser sizes here. There's two 958 TurboCasers, and on the other side, the small one is a 7-inch TurboCaser. But what I like about this picture is it shows you the reamer nose in particular, where the drillable part is, and that is the orangey part, which is a bronze alloy. So it makes it much easier to drill out. Next slide then. So before we do anything, once we might build the tools here in Aberdeen, we then flow test them to make sure that every component is working as it should, and there's no restrictions or no issues with the tool. And this just shows you an example of what it looks like when it's actually flowing. So when we do a surface function test on the rig site, this is basically what you would see when you look down into the bell nipple or down into the hole. You would have the tool nose just below the rotary table, so that you can actually see and visually quantify that the tool is rotating and flowing as it should do. So you can see that there's about 10% or 15% of the fluid that actually starts to come out between the reamer and the bottom of the stabilizer. And this is really basically to try and alleviate or if there's any buildup of cuttings that's built in there, to lubricate that area and to push out any cuttings that's built up. And as a result, when we go at high speed, you can see that centripetal force is just pushing the fluid out in a circular umbrella motion. And then beyond that, you can see that the ports in the nose, which was on the previous slide, you can see the fluid flowing out of there. It's not a jet, it's actually just a flow. Because on the 958s in particular, on this particular well that we were speaking about, the TFA is 10.55 square inches. So it's quite a large area. So it's not jets, it's ports. And as you can see in the right-hand picture, you can see the low flow rate, the fluid coming out of the ports. So on the next slide. This particular well that we're speaking about here, where we can see the first restriction that we came across, you can see in the left-hand side, the running in the hole, and the first two, we picked up the first two joints, not the first two, but you can see on there that we're picking up the joints and running in on elevators without any problems. And then we pick up the third one and start in the hole, and that's where we find the first restriction, the first slack off. So we slacked off a fixed limit, which was normally about 20 to 30,000 pounds of force. It wouldn't go down, so we try again, it wouldn't go down. So then we pick up and we kick in the pumps. And in this particular case, that we're pumping at 5 barrels per minute. And as you can see, very slowly we're slacking off and slacking off. Eventually slacked off, I think, up to about 20,000 pounds, and reaming at the same time. And the pressure fluctuating shows that the effective reaming or the reaming is effective based on the slack off weights. Then we got the joint down, picked up the new joint, made the connection, and then we picked up again off bottom, kicked in the pumps again to 5 barrels, and then start to slack off again. And it was far more, let's say, much more smooth on the next joint. As you can see, there wasn't the same fluctuations, but still needed to ream that joint all the way down to the bottom of the connection. Made up the next connection. In actual fact, tried going in on the elevators alone just to see if it would pass, and yes, it passed without any issue. So it just shows that there was maybe some sort of ledge or small area of restriction that it got through. So no issues, and then they started running in the hole without any issues after that. So on this next slide is basically showing the resultant or proving the point of how the tool works, and the fact that it works opposite to a PDM or an RSS. PDM, if you stall a PDM, you get a pressure spike on surface. With the turbines, you stall a tool and you get a pressure drop. So when you're reaming, you get resistance on the nose. So therefore it slows the turbine down a little bit more, so you get more fluid through, so the pressure drops on surface slightly. So this yellow part of the graph, this yellow line in the graph, is actually showing the standpipe pressure decreasing as we slack off and hit the restriction, okay, on the red line on the left. So as we're slacking off and taking, slacking off continuously, the pressure decreases and we're getting quite a stable pressure on surface, and we'll keep reaming all the way, and it proves that when we do pick up the string, then the pressure increases back to where it was before. So that's just a great indication of how the tool, or a result of how the tool actually works downhole. And so at this point, we'll hand over back to Em again for the next, or the second poll. So thank you.
Hi, thanks, Callum. Yes, so this is the second and final poll that you should see up on your screen right now. It is, have you experienced a casing liner run where the TurboCaser tool would have helped? If you could answer yes or no to that question, that would be great. So I'll go ahead and publish those results now. 80% have said yes, and 20% of attendees have said no. I'll hand back to Malcolm.
Thank you. So you can just see on the screen at the moment a little bit of recognition from the drilling engineer concerned with the case study that Callum presented to you there. He was hoping actually to have been available to take part in the webinar today, but he was caught up with some other work. But they're always very, very receptive to using our tools. We will now move on to the question and answers. If you have any questions you can think of and you'd like to ask them now, I will go and see if there's any. There's a couple already. So, how long does it take to drill out the TurboCaser after the cementing? We've, in the field, around about 15 to 20 minutes after the cement is in place. We've been able to drill out the TurboCaser. We've never had any reported issues of drilling out before. Also, what happens if the burst disc ruptures? Well, as I mentioned previously, if the burst disc ruptures, the flow path down the TurboCaser will move from the outside where the rotors and stators are, through the center of the power section instead. So there'll be no turbine movement of the reamer head. but the fluid will still be able to flow out of the reamer, as you saw earlier. Do we need to burst the disc to cement? No, you don't. As long as the pressure differential either side of the burst disc is below the burst disc capacity, then no, you don't need to. Next question. On the example shown, was it a ledge or cuttings bed? I don't actually know. This is Faisal's case study, and unfortunately he's, as I say, stuck offshore, so I don't know the answer. He would know the answer to that. Do you know, Callum?
I believe it was a ledge on that case, on that sample that we showed. It was just a ledge. Don't think it was a cuttings bed, but 100% I'm not sure. But it certainly wasn't any formation, let's say formation squeeze or anything. But I believe it was could well have been a ledge or a cuttings bed.
Okay. Next question. What is the recommended drill bit to drill out with mill tooth or PDC? Well, you can just go in with a PDC as your normal next section drilling BHA. You don't have to do any dedicated run to drill out. There'll be there's no recorded damage to the bits that have been used to drill out our turbo cases. I believe we have over 400 runs under our belt with these turbo cases, and we've never had any reported damage from any of them.
Yeah, exactly. And we have had milk tooth, but milk tooth will take a little longer to drill out.
Yeah.
That's the only thing.
Another question, have you done a job where the casing is also rotated as well? Callum, have you got any?
In certain cases, they'll try and rotate. We did have one job where we it was struggling to get through, and it was more to do with, I think, a bit of a pack off. So what they did is they rotated the casing in order to try and stir up a little bit more of trying to clear up that pack off, and it worked. But in some cases, yes, they may well want to do that to try and alleviate any sort of, let's say, pack off or something along that lines. Yeah.
Okay.
Or sorry, just one other thing to add to that is sometimes maybe if they're struggling with friction, for example, to try and push weight down, then to overcome the friction, then they may occasionally have to rotate the casing.
Another question, this could be quite an interesting one. Would you say the tool is more effective at removing cuttings beds or ledges?
Both really. It's effective at both. Obviously, ledges we can ride over as long as they're not too large. If they're a little bit large and you're struggling to get over, then activate the reamer and get over. If there's cuttings beds, then you activate, you pump, and stir up those cutting beds. But the beauty about the TurboCaser is that it rotates at high speed, so it may break down that cuttings sizes, and therefore then the benefit of that is that it will be suspended in the mud easier and pumped back to surface a lot easier and quicker than it would do if it was a normal size cutting. So it does alleviate both. I can't say which one it will be more effective at though, but it does both very effectively.
Okay, we have one final question, which is, can we pump LCM through the tool? Yes. Short answer to that is yes, we can. We have a lot of experience, and we do it as part of the flow testing before the tools go out. I believe the maximum concentration of LCM is about 50 pound per barrel, but yes, it's not a problem.
Yeah, and then the granular size, because we use a filter in the tool, then it would have to be slightly less than the filter size. And the smallest filter size we have is 1400 micron. So anything smaller than that, the granular size is fine.
that's the end of all of the questions we have for today. I'd just like to say thank you very much for attending the webinar today. If you do have any further questions, please get in contact with us. Emma will be sending out an email afterwards with the contact details and the feedback forms if you do wish to get in contact. But again, thank you very much for coming along, and we hope to hear from you soon.
Thank you.
Excellent. Thank you.